Alright, this problem is a tricksty trickster. Same deal, we want to solve it. We want to find the solutions to it, x-intercepts if you're thinking of this as a graph. And how do we do that? Well, I see I have a squared term, a not squared term, and a constant term, which means I'm dealing with a quadratic equation here. The problem is one of my quote variables is sine and the other is cosine. I put variable in quotes because they're not really variables as just the normal plain idea of variables, but they are the thingies that we're going to use to factor this quadratic. So what do we do? Well, I want them to both be sine or both be cosine, and the easiest way to make that happen is to replace the sine squared with a cosine squared. But I can't just swap them. I have to use a Pythagorean identity. And we know the first Pythagorean identity says sine squared of theta plus cosine squared of theta equals 1, which means sine squared theta has to equal 1 minus cosine squared of theta. So I can rewrite this equation, except instead of writing sine squared, I'm going to write 1 minus cosine squared of theta. And it is important that I put it in brackets or parentheses like that because I will need to distribute that minus 2. So then I'll have my plus cosine of theta equals 0, and now let's simplify. 1, distribute the minus 2 to that 1, we get 1 minus 2. Distribute that minus 2 to a negative cosine squared, we get plus 2 cosine squared theta plus cosine theta equals 0. So let's combine like terms. Let's call this 2 cosine squared theta plus cosine of theta. And a 1 minus 2 will give me a minus 1 constant term at the end. So I want to factor this, and you can totally think of this as 2x squared plus x minus 1 equals 0. I've made a little substitution. I'm saying let x equal cosine of theta. Because now we can think of this in terms of x's instead of cosines, so it might be easier for us to factor, hopefully. Well, how do we factor it? Well, we'll need a 2x. We'll need an x. These have to both be 1s to equal that constant term of minus 1, and 1 needs to be positive and 1 needs to be negative. Well, let's do it like that. And I put the positive 1 with the x term rather than the 2x term, because I know if I FOILed this out, I would get 2x times 1 is 2x, and then x minus 1 is negative x. 2x minus x is positive x, so I get the middle term I want. So this gives me two solutions in x. It's going to give me x equals 1/2. If you solve that first parenthesis there, 2x minus 1 equals 0, means add 1 over. 2x equals 1, so x equals 1/2. And then this other parenthesis will give me x equals negative 1. But I don't want solutions in x, I want solutions in theta. Which means, really, whoa, that was a lot of loud dogs. So what I was getting at is instead of x equals 1/2, we can substitute back in cosine of theta equals 1/2. And similarly, cosine of theta equals negative 1. So now all we need to do is think about the unit circle and where that happens. Well, where's cosine of theta equal to 1/2? Pretty sure we just did that on the last one, didn't we? No, that was negative 1/2. Alright, so where's cosine theta equal to 1/2? Well, it hits the 1/2 values at the pi over 3 lines, but it's positive. So we need just the right half of the unit circle. So we get those two values right there. Where's cosine of theta equal to negative 1? Well, again, cosine is x, so negative 1 would be all the way out over there, straight out to the left. So our solutions will be theta equals pi over 3. Theta equals pi from the negative 1. And finally, theta equals a 5 pi over 3. And those should be the 3 solutions to this crazy complex problem.